Okay, this is 6.6 homework help. The first problem wants us to state the domain and range of each of these functions. So we're looking at inverse cosine, inverse sine, and inverse tangent. Inverse cosine, well, the easiest way to get the domain and range for inverses is to recognize what the regular function looks like. The regular function is a sine, where the domain of that function is all real numbers, negative infinity to infinity, and the range of that function is negative 1 to 1. So if you want the domain and range of the inverse, you just flip these, because that's what inverse does. It switches the x and y and flips the domain. So it's negative 1 to 1 for the domain. Now, the range would be typically negative infinity to infinity for an inverse, right? Because it's a reflection of this line, and so the new function would look something like this, right? The problem is that's not a function. It doesn't pass the vertical line test. A vertical line would intersect this in multiple spots, meaning that's not a function and not helpful for us. So what we're going to do is restrict the range then. For cosine, we're going to restrict the range from 0 to pi. And that's on the formula sheet. It's not something you have to remember. If you pull up the formula sheet and scroll down, you'll see inverse cosine right here, and you'll see the range is 0 to pi. Okay, it's the same thing for the sine. The sine looks like this, same as cosine, just shifted over 90 degrees. When we reflect the line y equals x for our inverse, we get a function that looks something like this. It doesn't pass the vertical line test, so we know we're going to switch the domain and range again. Domain is negative infinity to infinity. Range is going to be negative 1 to 1. So we'll flip the domain and range so the domain goes negative 1 to 1. And then this time the range, when we flip these, we can't have all the real numbers again. So we're going to restrict it this time from negative 90 to 90. And once again, that's on the formula sheet, so you don't have to memorize that. Now the tangent's a little bit different. The tangent, normally looks like this, where it repeats so that the domain in here is restricted. The domain, has these undefined places at the asymptotes, which these are, by the way, where the cosine is 0. So like pi over 2, for example, would be right here. So with the domain and range, when we flip these, the range of the tangent function is all real numbers. So that's going to be flipped to our domain spot for the inverse. So the domain is going to be all real numbers, negative infinity to infinity. But the range this time we're going to restrict. We're just going to do this one right here from negative 90 to 90. We're just going to flip that part. So when you reflect this over the line y equals x, you end up getting something like this, where you can see the domain is going to be negative 90 to 90. I'm sorry, the domain is going to be all real numbers. The range is going to be negative 90 to 90. And that's right in the formula sheet as well. So you really don't have to memorize that, but I'm trying to show you can get it from looking at what we learned about inverse functions as well, hopefully. Okay, the next problem wants you to find these angles. Now, we know in order to find these angles, like for the first one, we'll just do inverse sine of this decimal right here. And that flips the domain and range, so that will give us this angle alpha. So we can just do that right in our calculator. Just do a second inverse sine of 0.31392. And make sure your calculator's in degree mode. This doesn't say. It says determine the angle. It doesn't say whether to be in degrees or radians. So that's a little confusing. But I've noticed that it does accept the answer when it's in degree mode, which would be 18.3 to 1 decimal place. Okay, same thing with tangent. Just do inverse tangent of 0.11 or 19982, and you get 11.3 rounded to the nearest tenth, 1 decimal place. And then for secant, that's a little trickier. For secant, we're going to have to do 1 over cosine of theta equals this number. And then we're going to have to flip both sides. So if we want to find cosine, we're going to have to do cosine of theta equals 1 over this number. And then do inverse cosine from there of this number. So that will give us our angle, which is theta in this case. So we can do that in the calculator. We want inverse cosine of 1 divided by, inverse cosine of 1 divided by 2.5913. And that gives me 67.3. Okay, the next problem wants the angle between 0 and 90, so we're going to be in degrees. And they give us the sine ratio, so we can do inverse sine to find the angle, beta. And once again, same thing in your calculator. Just make sure you're in degree mode, do inverse sine, and that gives you 6.373. Now, it's going to be picky. It says round to the nearest 0.001, so I'm rounding to this spot right there. And we would just do the same thing for cosine and tangent. Okay, the next problem is just getting the vocab straight. So we have this equation here, c equals sine of b. I'm going to write it like this. Sine of b equals c. Now, typically we use like theta, so we say sine of the angle equals the ratio, which is, opposite over hypotenuse. So that's what c is. It's the ratio of two sides of a triangle, and b is an angle, right? So we can represent that. Then it says that b is the angle, and the value of the trig function would be c in this case, which is opposite over hypotenuse for the triangle we could draw. All right. Now the next one's in inverse mode, so I'm going to put it regular. I'm going to switch this and make it tangent of p equals a, so that way I can see, okay, now it's tangent of the angle, which I usually use theta for, equals opposite over adjacent. So p is the angle, and a is the ratio. So p is the angle, and the value of the trig function would be a. Now the next one, arc cosine is just inverse cosine, so it's inverse cosine of a equals f, which I like to rewrite as cosine of f equals a, so that I can compare and say I usually do cosine of some angle equals the adjacent over hypotenuse, so I can see that my angle is f in this case, and the value of the trig function is a in this case. Don't be scared off by arc cosine. Some books just use different notation. So arc cosine means the exact same thing as inverse cosine, and that's how we're going to have to use it in Webwork when we go to enter in inverse cosine. Okay, the next problem wants us to find the tangent of 8. So that's just plug in your calculator, tangent of 8. It's going to give you 0.1405. And then the next two, arctan and inverse tangent, are the same thing, and they're asking for mine is the same number. So it's asking for the inverse tangent of 8 in both cases. So I can just write 82.87 for both of those. Or 875 to 3 decimal places. And then D, this is different. When it's written like this, when it's written tangent of some angle and then inverse like that, what that really means is 1 over the tangent of theta. So this -1 here is an exponent that reciprocates it. Okay, it's not the actual arc tangent or inverse tangent. Inverse tangent or arc tangent is typically written like this or like this. Okay, so this means something completely different. So in our calculator, we're going to have to do 1 over the tangent, which I did, 1 over the tangent of 8, which gives you 7.12 about. Now the next problem, in order to find an inverse function, I'm going to have to switch x and y. So I'm going to take the original function and just switch x and y. And then I'm going to solve by solving for y. So I'll subtract 4 from both sides. I'll divide both sides by 10. And then I'll take the inverse cosine. So I have an inverse cosine of x minus 4 over 10 equals 2y. Now just divide both sides by 2. And there's my answer right there for the inverse, which I'll write as f inverse of x. And then I'll also get rid of this and use arc cosine. So this is what I'm going to have to enter in. Now, the domain and range of the original function I'm going to find, the domain is going to be all real numbers. I can stick in whatever angle I want. But the range now, look at this thing's been stretched by 10 vertically. So the cosine usually goes, from -1 to 1. But this thing's been stretched, so now it's going to go from -10 to 10. -10 being down here, 10 up here. So it's going to go all the way like that. But it's also got this vertical shift upward of 4 units. So now it's going to go up to 14 and then down to -6 because it's been shifted up. So that makes my domain, or range rather, -6 to 14. And so that's going to be my domain, because when I find the domain of the inverse, I switch the domain and range. So I'm looking for -6 to 14. The range of the original function is the domain of the inverse. You switch the domain and range. And here's what it looks like entered in, the original one, because for inverse, that's a little tricky to enter in with parentheses. Okay, the next problem wants the inverse sine of square root of 2 over 2. I'm going to write that as the sine of theta equals the square root of 2 over 2. It wants an exact value, so I'm going to have to do this from the unit circle over here. So what I'm looking for is the angle where the sine is square root of 2 over 2. And it wants it in degrees. Well, the sine is the y value, so I'm looking for square root of 2 over 2, which is right here. So I can do 45 degrees there. Obviously, over here works as well, square root of 2, 135 degrees. But I'm going to try 45. And both work, 45 and 135. Now the next one would be the cosine of alpha equals square root of 2, or theta equals square root of 2 over 2. Right? All I'm doing is saying this is equal to theta, and then switching the theta and the square root of 2 over 2. So I'm looking for an angle where the cosine is square root of 2 over 2, and the unit circle, that's the x value, so that'd be right here. Or also down here would work as well. I'm sorry, right here. So either one, but I'll just use 45 again. And the next one, cosine of some angle has to equal negative square root of 2 over 2. Well, I'm looking for the x value where that's true, and that's right here at 135. Or obviously down here as well at 225. And then the last one, the sine of some angle has to be negative square root of 2 over 2. That's down here. So I'm looking at this or this point right here. So 225 or 315. I'll just use 225. Okay, the next problem is a little tricky. We have to take this, it wants the secant of this angle right here. It wants an exact value. So that's actually an angle. Arc tangent of 2 is equal to some angle. I'm going to call it theta. And I'm going to write it like this. Inverse tangent of 2 equals some angle. Then I can write it like this. The tangent of theta equals 2. Now, I'm going to draw a reference triangle with that satisfies that. That reference triangle would have to be in the first quadrant. I know that because the range of the inverse tangent on your formula sheet is negative 90 to 90. So the values that I get out have to be between here and here. And the tangent in this case is positive, which means that sine or cosine must be positive. So it needs to be in the first quadrant right here. It's opposite over adjacent. So the hypotenuse would be the square root of 5 with the Pythagorean theorem. And now I can do the secant. The secant of this angle, this is my theta right there. Now the secant's really 1 over cosine. So what I really want is, since I called this thing theta right here to start, I want the secant of theta. I want 1 over the cosine of theta, which is really 1 over cosine to be adjacent over hypotenuse, so 1 over the square root of 5, which simplifies, if I multiply by the reciprocal, simplifies to the square root of 5. All right, now the next one might be even more tricky. I want the cosine of 2, and I'm going to call this angle right here, because inverse sine is an angle. I'm going to call that theta now. So it's going to be cosine of 2 theta. Now, I'm going to write that separately. Theta is equal to inverse sine of 5 over 13. So what that means is the sine of theta is 5 over 13. And I'm going to graph that in the unit circle to find out that reference triangle. That's going to be in the first quadrant because sine is positive. So it's going to be 5 over 13. And, I know the numbers I can get out for here for that value have to be between negative 90 and 90 off the formula sheet. So therefore, I have to be in the first quadrant where the sine's positive and I'm between negative 90 and 90. Now, if I do the Pythagorean theorem, this would be 12. So this is my angle theta. Now, I want the cosine of 2 theta. Now, that's on the formula sheet as well. If you scroll down even further in the formula sheet, you'll see these cosine of 2 angles. We're actually not going to use these till next chapter, so I wouldn't put this question on the test yet. But what you would do is use any one of these. I'm going to use the first one, cosine squared of the angle minus sine squared of the angle. So it'd be cosine squared of our angle, which we call theta, minus sine squared of our angle, which we call theta. Now, cosine in this case is adjacent over hypotenuse, which is 12 over 13. I'm going to have to square that. Sine is opposite over hypotenuse, which is 5 over 13. I'm going to have to square that. This turns into 144 over 169 minus 25 over 169, which turns into 119 over 169, and that's my answer. That goes right here. Okay, the next problem is really tricky. It wants to know the domain and range of this function right here. So I'm going to take a look at the regular inverse sine function first. Okay, the regular inverse sine function is graphed right here for you. If you can start making a table if you wanted to. If you make it sine of, y equals x, and you plug in negative pi over 2, you're going to get 1. So that's this point down here. And this point up here is the other point. Then if you plug in positive pi over 2 into this, you get positive 1. So the graph is just one cycle of a sine. Normally it would continue on forever, but we cut off the range so that we have a function. Now this one is different though, because this one has been stretched. In fact, I can write it as 3 times x plus 1/3 right here. So this is a horizontal shrink of a factor of 3. So the domain would now be negative 1/3 to 1/3 because I have to shrink it. And then also this shifts it to the left 1/3. So now I have to subtract 1/3. So it would be negative 2/3 to 0 here for the domain. And then nothing's happened to the range, so that can stay negative pi over 2 to pi over 2. Now you can always double check that on Desmos, which you probably wouldn't be able to do on a test, obviously. The range does go from negative pi over 2 to pi over 2, but the range does go from negative 2/3 to 0. Okay, the next one here, the answers, I'll have to go over this one in class. Okay, and then this one's 37, 25, 100. They undo each other. The one to pay attention to is this one because the range is from 0 to pi, so it has to be positive. I'll explain this better in class if you want. And then here's the last one.